Okay, today we're going to talk about the probability of two events happening. And this covers the last integrated algebra standard of the year, the statistics standard 23. So the integrated algebra standard statistics 23, and it has to do with probability. So we're going to look at a series of independent events, dependent events, mutually exclusive events, and events that are not mutually exclusive. All right, so there's two types of, when events occur, two or more events occur, I like to separate them into two categories, the or category, and later on I'm going to talk about the and category. So the or category says, okay, so this is an example of the or category. Let's say that 24% of the students at a local high school are seniors, and 16% are juniors, 34% are sophomores, and 64% are freshmen. And if I ask you a question, if a student is chosen at random, so let's just say that they're all in the auditorium together, and you choose a student at random, what is the probability that they are a senior or a junior? Okay, so this is the or question. Now, senior or a junior means that I'm going to look at the two percentages together. With the or question, I add. Okay, because they could either be a senior or a junior. And by the way, you can't be both a senior and a junior. So being a senior and a junior are called mutually exclusive events. Okay, because they can't happen at the same time. That's not always going to be the case, but for this it is. So a mutually exclusive event are events that can happen at the same time. Okay, so for this it's pretty simple. I would just look at the probability of being a senior. I'm going to represent that in terms of a decimal, so 0.24. I'm going to add that to the probability of being a junior, which is 0.16, and I get 0.40. If I turn that into a percentage, it would be 40%. So if I just chose a student at random, there's a 40% chance that they would be either a senior or a junior. Okay. Now our next example is another type of or question. Let's say that there are 5 types of fish in the tank at the pet store. 10% of the fish are tiger striped, 20% are angelfish, 15% are catfish, 30% are tetra, and 25% are zebrafish. Let me just quickly make sure these, I wrote this really quickly, make sure they add up to 100. So it's 30, 60, and 40. Okay, so that's 100. Good. You just want to make sure of that because the question would be incorrect if it didn't add up to 100%. And if Joe randomly nets a fish, what is the probability that he gets a zebrafish or a tiger-striped fish? Okay, so again, this is the or question. And the first question you want to ask yourself is it mutually exclusive to be a zebrafish and a tiger-striped fish? In our case, yes, it is mutually exclusive because you can't be both at the same time. So all I have to do here is, again, add the probabilities together. So I have zebrafish, which is 0.25, plus tiger striped fish is 0.10, and I would get 0.35 or 35%. So there's a 35% chance that if I just net a fish randomly in this tank, it would be either zebra or tiger striped. Again, those are mutually exclusive. Let's talk about one that is not mutually exclusive. So let's say in a school there are 45 students in science class, 34 students in English, 8 students in both, and 21 students in neither class. If a student is picked at random, what is the probability that they are in science or English? So again, this is an or question where I'm going to have to add. But I have to be very careful when I add because remember, I don't want to overcount students. So if I just looked at the students in English, 34, and the students in science, and I added those together, so 45 plus 34, I get 79. But I'm overcounting because some of the students in science are also in English. All right, so what's a better way to do it is to either make a Venn diagram. So here we have, let's say, science class, and we have English. And with a Venn diagram with an overlapping, always start with the overlap. So if there's 8 students in both, that means that if there's 45 in science, I have to take that 8 from the 45. And that would be 37. So 37 are in science only. If there are 8 in both, then I have to take that from an English class too. And that would be 26. Okay. And so in terms of adding them all together, I want to just add the 37, the 8, and the 26, okay? And you'll see that this figure right here has been overcounted by 8. You'll see that. All right, so 37 plus 26 plus 8. Okay, and this would be 21, carry the 2, and so it's 71 here. Okay, and you'll see the difference between 79 and 71 is those 8 students, and that's because I had overcounted by 8. And that's because being in English and being in science are not mutually exclusive, meaning there are students who could be in both. Unlike our example with our fish, where the fish could either be one fish or another fish, or juniors and seniors. You could be a junior or a senior, but you can't be both. Okay, so be very careful of the or statement, because you may have overcounted. If the events aren't mutually exclusive, then what you need to do, and actually I haven't answered the question because I haven't found the probability, but I just wanted to count the students who are in science or English or both. So you want to be very careful that you don't overcount. Okay, so the probability would be, in order to get the total probability, 71 is my favorable event, and I need to make sure to add all the students together. So let me finish my Venn diagram here. There's 21 students in neither class, okay? So I want to add 21 to 71 and get 92. So there's 92 students all together that we've counted, and 71 are in, oops, sorry, that's 92 right there. And 71 are in English or math, English or science, or both English and science. The or statement means one or the other, or both. Sometimes people are a little thrown off that it also can mean that they're both. Okay. Now I want to go to something called the and statements. With the and statements, you are going to multiply the probabilities together. Okay, so these are the statements that have an and in it. So let's look at this. What I've done is I've changed the problem that we just had previously. Okay, and I've made it to say, instead of or here, I've made it to say and. So I want to pick students at random, and I want to know the probability that there are in English and science. Okay, so in that case, I only want those 8 in between. Okay, so I have, there's only 8 students who are in both out of the 92 students altogether. And the reason why I say that you have to multiply is because the probability of being in English, well, actually, this is not a very good example because we could have just easily counted. So when you can just count with the and statement, just make sure, don't make it overly complicated. I can just count that there were 8 there, or they gave me that there were just 8 in both of them. So I know there were 8 out of 92. All right. But again, if you were just given this question out of nowhere, make sure that you make a Venn diagram, because you want to not overcount the students. I mean, to get this 92, you had to really make sure not to overcount the students who are in English and in science. Okay, now there's another statement that's an and statement in disguise, is what I like to call it. So let's say that they ask you about 3 fair dice that are thrown. The probability that all 3 dice shown are 5. Okay, now I call this an and statement in disguise because what you are looking for is so let's say that you have die 1, die 2, and die 3. You want die 1 and die 2 and die 3 to all be 5. So you're looking for an outcome on all 3 of the dies all together. Okay, so this is your and statement. It's not that one or the other or the last one have 5. So it's not like you're throwing 3 die and you're looking that if there's 1 or more 5s on there. You want all 3 of them to be 5. So this is your and statement. So this is when you're going to multiply the probabilities. Okay, so let's get the probabilities of each one. The probability of getting a 5 on the first die is 1 out of 6, because there's one side that displays a 5. The probability of getting a 5 on the second one is 1 out of 6. And the probability of getting a 5 on the third one is 1 out of 6. So when we multiply this all together, this would be one outcome out of, okay, so 6 times 6 is 36. 36 times 6 is 216. Okay? And that's our answer. It's 1 out of 216. It's a pretty small chance of it all getting 5. Okay, an independent event. So these throwing a dice are independent events because each throw of the die does not affect one another. So what die 1, if die 1 gets a 5 on it, it doesn't affect the outcome of die number 2. It's not like the dice change shape depending on what the previous die was rolled. Okay, the die remains the same whether or not you throw it once or twice, or if you have 3 dice that you throw once. Okay, so throwing a fair die does not affect one another, so this is called an independent event. Let's look at another and statement in disguise. Let's say that a bag contains 1 white marble, 1 red marble, 1 yellow, and 1 blue marble. What is the probability of pulling out a white marble, then a blue marble, then a yellow marble if you replace the marbles after each draw? Okay. Now, these are independent events because you're replacing the marbles after each draw. So you have this bag, right? You have this bag right here. And inside you have 1 white marble, so I'll just outline it right there. You have 1 red marble, so let's get a red marble in here. You have 1 yellow, and you have 1 blue. All right, so you have 4 marbles altogether. And you are wondering what the probability of pulling out a white one, and then a blue one, and then a yellow. You see how I'm using and in between all these things? So these 3 events are together. When you say them together, you want them all to happen together. So you're using the and statement. It's not like you want it to be a white or a blue or a yellow. You want 3 pulls to be made, and you want one of them to be white, and one of them to be blue, and one of them to be yellow in that order. Alright, so this right here is going to be the multiplication. You're going to have to multiply the probabilities each time. So first you figure out the probability of a blue marble. So you have 4 marbles in there, and one of them is blue. Then the second event is the yellow marble. Okay, again, you're replacing the marbles, so you start with 4 marbles, and one of them is yellow. Whoops, actually this is supposed to be the white marble, the blue marble, and finally the yellow marble is also 1/4. So 1 times 1 times 1 is 1, and 16 times 4 is 64. Okay, so it's 1 out of 64. And these are independent events because pulling a white marble out for the first one and replacing it did not affect the probability of pulling the blue marble out on the second one. Okay, and since you replaced it, it didn't affect pulling the yellow one out on the third one. These are called independent events. Here is something that we call a dependent event. Let's assume that, again, we have the same bag of marbles, 1 white, 1 red, 1 yellow, and 1 blue. Okay, and you want to pull a white one out. So you want white, and then you want blue, and then you want yellow, but you're not going to replace the marbles after each draw. In this case, pulling a white marble out in the first pull will affect the probability of pulling a blue marble out. So the probability of pulling a white marble out in your first pull is 1 out of 4. One of them is white out of 4 total. So that one's gone. You assume that the white one's been pulled out. Now when you pull the blue one out, there's only 3 marbles left to pull out. Okay? And one of them is blue. Alright? So notice that the denominator changes. That's because these events are dependent, because you're not replacing them after you do that. Alright? And then you assume that you pull the blue one, and the probability of pulling a yellow, now there's only 2 left, and one of them is yellow. So again, your denominator changes. So here I'm multiplying 1, and then this is out of 24. Okay. Notice that this is a greater chance than 1 out of 64. So if you don't replace the marble, it makes sense that you become more likely to get another color marble because you're not replacing the one that you pulled out, right? So the denominators here are all changing. Okay, whereas they were all 4s before, they're now 4, 3, and 2. So the denominator is smaller. That makes the entire fraction bigger. So it's more likely that this will happen than this. Okay, and that's the end of our lesson today. So I just want to make sure you understand a lot of these combined events can be broken down into two types of events. The ones that use an AND statement where you have to multiply, and the ones that use an OR statement where you have to add. Okay, so you add the probabilities in an OR statement and you multiply in an AND statement. It's a pretty simplistic way of looking at it, and it really, when you get to Algebra 2, you're going to find much more complicated ways of looking at it so that you can do more complicated probability questions. But for integrated algebra, you only really have to understand how when you should add the probabilities together and when you should multiply them.